Oh, there it is. Hey, hi, everybody. I guess this is our first in-person seminar in quite a while. It's a real party scene over here. Thanks for those of you who are joining remotely. You're really missing out on the full vibe, though. I'm really happy to have a speaker that I think is an excellent way to start off in-person seminars again. Pratik Chaudhari is well, I got to know him when he was a PhD student at UCLA. He's done a lot of amazing work on topics that I find very fascinating: information theoretic, machine learning, and some, I think, really relevant for modern machine learning practice stuff that we're going to hear about today. He's now a professor at UPenn, and I'll let him take it from here. Thanks, Pratik.
Thank you for inviting. Thank you for hosting. Thank you for introducing. I'm excited to be here. I know some of you in quite a lot, so that should be fun. Let's keep this conversational instead of a seminar. So I'm totally happy if you interrupt me anytime with questions. Today, I will tell you a little bit about some perspectives, roughly speaking, that I have come to after looking at problems at the intersection of optimization and generalization in deep learning. And so this is a new take on some old results, some new results that shed light on understanding the old results better. And I want to walk you through it and see what you think about it. So there are really two key questions in deep learning today, right? We know that the network is huge, lots of parameters trained on lots of data on an non-convex function. So this should be very difficult to optimize. Clearly, it is not. Most of us can train a decent neural network on a laptop. And the question is, why can we train efficiently? The second question, which we'll actually focus on in this talk, is everyone told you that if you have 10 data points, you should not fit a 25-degree polynomial to these 10 data points. In deep learning, we love to do this, and we do not suffer from doing this. Why is it that deep networks do not overfit, even if there are many parameters? Okay, so this is a question that I want to think about in the next hour or so. And just to lay the context, I will show you some anomalies that were surprising to us when we found them. These are not the only anomalies about deep learning. There are many others, and there are also many others that have built upon this. But these are some results from my past work, and I will use them to give some context to what we talk about. Okay. So here is one picture. This is these are the eigenvalues, the histogram of the eigenvalues of the Hessian of a convolutional network on MNIST. So simple experiment, train a convolutional network, wait for the training loss to stabilize, and then calculate the Hessian. And one thing that we were very surprised by is why is it that such a large fraction of the eigenvalues is essentially zero? About 95% eigenvalues were very close to zero in this experiment. There is also some large positive eigenvalues. So this is a region where if you stand at that place, many directions in the loss function does not increase locally. And then there are some directions in which it increases. There are also some directions in which the loss decreases. So this is not a local minimum, certainly not a global one. It is a saddle point. It is more or less a benign saddle point. There's about one order of magnitude fewer negative eigenvalues than positive ones, and they're also smaller in magnitude. So you end we notice that typical training methods, SGD-like training methods, if you change the algorithm, the size of the peak changes a little bit, but the shape doesn't really change so much. Irrespective of the data set or irrespective of the architecture, the Hessian does seem to look like this. And we are trying to think, okay, so we know that these algorithms seem to converge to such regions. Some basic calculations in statistical physics indicate that not all regions should be like this. In problems in combinator optimization, such regions which are locally very flat or locally very entropic are very rare, are exponentially rare. So larger the system, the fewer such regions. So it is very surprising if you come from that perspective as to why your training method in these dimensions converges to such regions, and more importantly, why such regions generalize well. So if your training method does not converge to such regions, if the peak is a little bit smaller, then you get slightly worse validation error. This is also something that we have noticed. Okay. And then over the years, we kind of cooked up algorithms that amplify such effects. So we built objectives that are different from the training loss, that are kind of putting bias on regions that are such wide regions. And if you minimize those objectives, you will see that. So the black line is SGD for a neural network on MNIST. The purple line and the green line are these fancier methods, and they work very well. So they are about 2 to 4 times faster than SGD. So still, to my knowledge, some of the only algorithms that improve upon the speed of SGD and also improve upon generalization. Okay. So if you amplify this effect of reaching wide regions, you can do well. It is surprising that as to why you reach wide regions. So here is one way we began to think towards the end of my thesis work, essentially. So in a non-convex energy landscape, it doesn't mean very much to say I reach a critical point, or this is how fast I reach a critical point, because there are many, many critical points in your neighborhood. You will fall into the first ditch that you encounter. There is nothing to say after that. Okay. So you can kind of flip the question and ask a much more abstract question and say, I have 1 million initializations of my training process. At the end of time, they converge somewhere. I would like to calculate the distribution induced on the weight space by my training process. This is, in some sense, a pointless question because it happens, this distribution occurs at the end of time. But maybe if I understand something qualitative about the shape of this distribution, I may be able to say what happens to one particle of SGD across many, many experiments. Okay, so it's a more of a mathematical treatment, but here is how it works. So you can write down a model for SGD, and this looks like a drift diffusion equation. So dx is the increment in the weights, x are the weights here. Gradient of f is the trailing loss. So if I just gave you the first 2 terms here, this would be exactly gradient flow, continuous time gradient descent. But we know that SGD is not gradient flow, so let's write it down as a Brownian motion term. So W is the Wiener process, and it is not an isotropic Wiener process in the sense that it doesn't perturb the weights equally in all directions, but it perturbs it using this matrix D. So D, you should think of it as the covariance of the mini batch gradients. Eigenvalues or eigenvectors of D corresponding to large eigenvalues are directions in which noise is very powerful. There could be other directions in which noise doesn't do very much, and so those directions would be just gradient descent. Okay, and this is what makes understanding these kinds of equations challenging. But here is one general method to study such equations. It is what is called a Fokker-Planck equation. It is known by many other names in other fields. But roughly speaking, you want to write down an object, which is the distribution of weights at time t, which I denote by rho here. And you can obtain a partial differential equation up to a first order approximation that says the temporal derivative of rho, which is rho sub t, is equal to the sum of 2 terms, the divergence of the sum of 2 terms. The second one is easier to understand, so let's look at that first. So most of you have seen a heat equation. The heat equation tells you how molecules of perfume spread apart in the room when you open the bottle of perfume in one part of the room. And that is the object of the second term. The first one is kind of like you taking the bottle of perfume and then throwing it across the room to your friend, or more appropriately, 1,000 copies of you throwing the bottles of perfume to your friend, because this is the gradient of a potential. So this tells you how stuff moves in bulk, the blue part, and the brown term tells you how stuff diffuses around these bulk motion. So very, very analogous to how this stochastic differential equation behaves. Stuff moves in bulk because of the gradient, stuff moves diffuses because of the diffusion. And we would like to understand the solutions of this partial differential equation, the steady state solutions. Okay. Here is one example. If the diffusion matrix, let us call it B, the covariance of minibatch gradients, if it is identity, then this is a very well understood equation. It is called the classical Fokker-Planck equation. And for such equations, people in optimal transport have built a very nice way to understand them. You can say that the solution, the one where the left-hand side is 0, is given by a steady state distribution rho SS, which is the solution of a variation problem that pays attention to two specific things. The second one is an entropic term, which tells you that, oh, if I start at one place in the weight space and I run for infinite time, I spread apart, just like the molecules of perfume spread apart everywhere. That is coming from this part term. So it is, we believe, or we like to think that SGD does implicit regularization because of the noise. This is the implicit regularization, just coming from the noise. The first term is the average of the training loss of weights that are sampled from this distribution rho. And that is again very natural. I train many runs, this 1 million runs of SGD, all of them will converge to regions where the loss is small. So on average, you are minimizing the loss. But you're also spreading as much as you can in your parameters. Okay, so this balance between some kind of an energetic term and some kind of an entropic term is what the SGD in this variational sense achieves. Okay. If you have a more general Fokker-Planck equation where D is not equal to identity, if we did not have this blue term, then this is what is called the Laplace-Beltrami operator. It is like diffusing on a manifold, and that is again like a very well understood of how diffusion occurs on a manifold with a metric D. If you have both these terms, then it becomes a little hairy to calculate the steady state distribution. So we had to do some acrobatics, but you can get a similar variation principle that looks as follows. So the steady state distribution here now is trying to balance two terms. The second term is unchanged. It is still an entropic bias. That shouldn't be surprising. After all, noise is noise. It will powerful in some direction locally, so be it. So it still has this quality of spreading apart in the parameter space. But the first term is the average of a function phi that need not be equal to your training loss. Okay? In fact, you can prove that if D is equal to identity everywhere in your weight space, then and only then this phi equals your training loss. And this is very surprising because you are taking mini batch updates on your training to minimize your training loss. But somehow, because this noise doesn't let you move equally well in all directions, you end up reaching the critical points of some other function phi. And in simple cases, by taking, let's say, quadratic approximation, we can calculate the difference between phi and f. That's easy to do for simple cases. In general, it is very hard. But the moral of the story is that this matrix D controls how the critical points that you reach, and they can be quite non-trivial. So it's very surprising to me even still that you're taking mini batch updates on your loss, you end up minimizing some other function. Okay. No one would believe this. People still don't. But here is one plot for how badly non-isotropic D can be. So the rank of the diffusion matrix, which is the, again, variance of the mini-batch gradients, is as small as 0.5%. So not only it is not identity, it is ridiculously not identity. So these effects that we see as coming from the noise acting in different ways in different dimensions or different directions, they are very strong. You can have SGD converge around saddle points. Another thing that people have noticed over the years is that we imagine training as a little ball that bounces and then reaches some place and stops. That is not how training is. Training in what will happen is that keep on evolving without ever reaching anything. So in fact, trajectories of SGD are trajectories which keep the function be constant, and they can evolve in a subspace of the weight space forever. Okay? So these are very surprising things because they defy our intuition from convex optimization. And roughly speaking, this is where I finished my thesis. I said, I don't really understand this. There is weird things that we found. Maybe we made some reasonable use of them by cooking up better algorithms. But the fact of the matter is we don't understand why even something as narrow as training a neural network is showing this weird behavior. Yeah. The way I think about it now is that we don't understand it because we did not look in the right places. So there is one person who says neural networks are so cool and so magical because of overparameterization. That is the real thing. So I'm going to study that. Then this other person says, oh, SGD is the real magic. There is something very deep about the stochasticity of the minimized gradient. So I will study that. That has to be the answer to the question. Then there is this other guy who says, oh, like neural architectures are so interesting because rest nets work clearly, non-rest nets work much worse. So there has to be something deep about the architectures we build. But then there is this other guy who comes in and says, VI transformers work just as well as convolutional networks. So why should I care about architectures? And notice that these are all guys because this is maybe like a 2000-year-old comic. Depends on where you come from. It is either a Persian six blind men or Indian six blind men. But what I would like us to do, or I want to convince you to do, is look at the elephant in the room, which is every single one of these models was trained on the exact same data set. And that is probably controlling all the things that we see. And if you understand the data better, then maybe we can understand neural networks better. Okay. So this paper was led by Rubing Yang, who is a student in my group. She's doing her PhD in applied math, and Jialin Mao, who is also doing her PhD in applied math, helped her on this. It is an archive, so feel free to ask me any questions if you find after reading them.
Are you in the applied math department?
No.
Oh, okay. You just got students from applied math.
Yes.
They were the only ones who could keep up with you, maybe.
Not really. So the applied math program at Penn is like a little special. So it takes in 5 students every year. That's it. And so these are usually like creme de la creme. And they get very attracted by this kind of work because they want to do deep learning and then they see, oh, like I understand the stochastic processes so well. So that is how, for instance, Rubin came to my office. He says, I want to work on, I don't know, like Maclin-Luxlow equation or some such thing. And I said, oh, maybe that, but I may not be the best person to help you there. But yeah, so it has been very nice working with students from applied math. Okay, so let's begin with an experiment as usual. I want you to first focus on the blue line here. The blue line was calculated as follows. So you take CIFAR, these are RGB images, 32 pixels. So there is 3072 dimensions in the data. And you arrange it in a big matrix where every column of the matrix is one image. So number of columns equals 50,000, the number of images, the number of rows equals 3072. And the blue line, the dotted blue line, are the eigenvalues of X transpose. So they are the eigenvalues of the correlations across different pixels in CIFAR. We know, for instance, that images have correlations that decay as a power law. This is that power law. Okay. What people haven't noticed is they decay in a log linear fashion. In fact, we believe that images are low rank. They're not really low rank. They're effectively low rank because the power in the different eigenvalues, it drops very sharply after about 100 dimensions in CIFAR. For MNIST, if you're curious, it is more like 3, this drop. And what is surprising is the eigenvalues drop by about 8 orders of magnitude across the 3072 dimensions. And the shape of the eigenspectrum could have been anything. It could have been quadratically sloping down like this, but it is linear. Okay? So this is just about data. There is nothing, no machine learning. This is like a 2-line experiment you can do. What is surprising is that if you have data like this, then essentially every quantity that you can calculate on a neural network trained on this data. So this is a wide rest net, a reasonably large one. And the orange line are the eigenvalues of the feature information matrix. The green line is the empirical Fisher. Hessian is the red one. So Hessian is a little more expensive to calculate. So we did only 600 eigenvalues, let's say. So this is the exact matrices without approximations, but the eigenvalues. And essentially, every single quantity that you care to compute or you can compute has the same shape of the eigenspectrum. They all fall sharply in the beginning, and they all decay in a log linear fashion. In fact, if you focus on the orange line, you don't see the orange line, it is just behind the green one here. For a linear model, linear regression, the Fisher information matrix is equal to XX transpose, the data matrix. This is, I can write down a little calculation. So for linear regression, it is equal to XX transpose. So for linear regression, the orange line should be identical to the dotted blue line. What we are seeing here is that for a neural network also they are pretty damn close. So these models are like secretly quite linear, which a lot of people believe now anyway. So the way to understand the implications of this are as follows. So Fisher information matrix governs the curvature in the output space of a model. So how quickly do the outputs change if I perturb my weights? The Hessian governs the curvature of the loss function. How quickly does the loss change? It's the average of the discrepancies of the outputs with respect to the ground truth, right? So both of these quantities are telling us about how the outputs change when I perturb the weights. Eigenvalues that are small for the Fisher, the eigenvectors corresponding to these eigenvalues, consist of combinations of weights that I can change by many, many orders of magnitude without changing the output of the model. Okay, this is just imagine you standing in the space of functions, and then there is one direction which is very flat, and I can move in that direction by changing the weights of my model. It is not one weight vector, it is a combination of the weights. I can change them by huge orders of magnitude without changing the output. Okay, that is why we call such things sloppy. And we also call them sloppy because some physicists a couple of decades ago started noticing such patterns in data, and they also came up with stuff like sloppy. It is called these kinds of eigenvalues are called sloppy because these ones you can call them stiff that way. Okay. The same thing is true for the Hessian. Essentially, there are many directions that we saw are flat. In the first plot of the talk, I was plotting the histogram, so I did not notice this log linear business. I wish I had plotted the eigenvalues instead of the histogram, but you will see so many papers studying the Hessian and plotting the eigendensity, because results in random matrix theory tells us something about the eigendensity. But the way to understand this, I think, is that the eigenvalues or the spectrum of the eigenvalues themselves is also quite important. With the eigendensity, all these things get clubbed into a huge spike that you will see in something like Marchenko-Pascoe distribution, which is the law of the eigenvalues of covariance matrices. Okay? Then you won't see any patterns there. Another thing that I want to emphasize is both Fisher and Hessian lose rank because of overparameterization. But the important thing is not to worry about the eigenvalues that are zero. They don't do anything. The output doesn't change if I move along the symmetries of the manifold of functions. These are the zero eigenvalues of Fisher. So why should they govern generalization? We should worry about the non-zero parts of the eigenspectrum. That probably is more important. Okay. So as I said, this is nothing specific about deep networks. Everything that we have said has been noticed many, many times over. And let's take one example. So a cell signaling network is inside every cell of your body, there is a bunch of proteins that interact with each other. And some proteins, they control enzymes at the end of this interaction. Some others, like they control transcription factors, etc. But you should imagine a system of differential equations where, let's say there are 10 equations with typical outputs, and then every equation is a function of a few proteins. And the parameters of the system are the rate constants that tell you how much of a protein you need to create a tiny change in the output, and the concentration of the protein itself. Now, biology has evolved in such a way as to keep the output of systems like this regulated, even if there are huge changes in the inputs of the system. So a bad example that I usually give is that suppose you did not eat all day today, you don't want to not fall asleep. You still want to go to sleep. And otherwise, your brain will be tired. These systems are such that they are resilient to huge changes in the proteins. They're resilient to huge changes in the rate constants of those proteins. They multiply each other, so they're essentially equivalent in terms of thinking like this. So the y-axis is the eigenvalues of the Fisher information matrix of a model that was fit to data of a cell signaling network. In this case, it is ER. And you will again notice that eigenvalues are spread uniformly across an exponentially large range. So if you take the logarithm, they are log linear again. Okay, so cell signaling networks are sloppy. Many other things are also sloppy. So for instance, this is the Ising model, and this is the Ising model gives you a probability distribution as a function of the spins. And so you can write down a Fisher matrix for the probability distribution as a function of the coupling constants. And this is the Fisher matrix. And so for the physicists in the room, these two large eigenvalues will correspond to the average magnetization and the temperature, which are like two defining parameters of the behavior of the model around a critical point. So you can identify which parts of the behavior of a system are robust by looking at the large eigenvalues. But weird systems, so this is a system of like magnets that control an accelerator, and so there are many parameters to the magnets, and typically like you would tune them to control like the magnetic field inside the cavity precisely. That is also sloppy. So there is every time you see a system where you are using data from some physical process, we have seen sloppy spectra. In fact, I have been searching for, roughly speaking, 1 year now. I haven't seen a data set. It does not look like this. Okay, sound, text, images, certainly. Here is one concrete calculation. So you can prove that the trace of the Fisher and trace of the Hessian are upper bounded by the trace of the data correlation matrix. So this is exactly the matrix whose eigenvalues we plotted, the dotted blue line. And the way to understand this calculation is that there is a bunch of multiplier terms that come from the weights. But if I were to take one neural network and then stretch it out to be infinitely wide, then the blue term don't change because it is the data term. If I impose something like weight decay, then I can control the second term also, depends on weights. So even if the network is infinitely wide, the product of the weights can be controlled. In that case, the eigenvalues of the Fisher, the number of eigenvalues of the Fisher keep increasing because the network becomes more and more wide. They have to decay also. So the trace of the Fisher is upper bounded by the trace of the data matrix. If I take an infinitely wide network, then I can also show that the eigenvalues of the Fisher decay. If I take a network with random weights, then you can also show that you can control the spectrum a little more precisely. And the moral of the story is that the trace is controlled. You can go a tiny bit deeper and say, after all, I was making statements about the spectrum, right? Not just the trace. So controlling the spectrum in general is very hard. You either have to assume that the weights are random, which is not that interesting, or assume that the network is infinitely wide, in which case it becomes linear, so there's nothing to show in some sense. But here is one intermediate regime. So this is a general result, but it is only about the blocks of the Fisher on the diagonal of the Fisher information matrix. So we say that we look at the correlations of every layer with itself and ignore the off-diagonal terms. And when I say spec, it is a sequence of eigenvalues of that particular block. Okay, the entire sequence is upper bounded by, again, like some stuff that depends on the weights, but the spectrum of the activations of that particular block. So the first eigenvalue of that block of this block in the Fisher is upper bounded by the first eigenvalue of this stuff and the activations. Same for the second, same for the third, etc. Okay, and so what this tells you is that if the activations are sloppy, if the activations slope in a log linear fashion, then the eigenvalues of the Fisher will also have to decay with this. Okay. So we cannot prove this in full generality because we are throwing away the off-diagonal terms, at least for the blocks, it makes sense. In some cases, like the off-diagonal parts of the Fisher, you can show, at least for linear networks, they don't matter, off-diagonal blocks. And we saw in the first picture of the eigenspectra that the activations are also sloppy. Doesn't matter which layer you evaluate them for, they are sloppy. And this has very useful implications for fields that go from like metric learning to looking at relationships between different representations learned by the network, etc. These things are not nice and Gaussians that we believe them to be, but they are like a very long and elongated Gaussians. Here is one application. We look at PAC-Bayes bound. So I know most of you here must have seen this many times. So Q is a distribution on the space of hypotheses. Little e of Q is the average test error of a hypothesis drawn from Q. E hat n is the average training error. And so typical PAC-Bayes results, let's say McAllister's, will go as like this. The average test error is upper bounded by the training error, average training error, plus some term that tells you how complex Q is. It is the Kale divergence of Q with respect to some prior P is telling you how many different hypotheses Q puts its mass on. And then you have like the concentration term, which is 1 over square root. Okay. So the name of the game in using such theory for neural networks is to be able to write down a Q that says, for this Q, I can show that this bound makes sense, or this bound is tight or not vacuous, etc. People haven't managed to do that yet. In fact, like when we first started plugging in numbers into this so-called theory, we realized that the test error is, let's say, 1%, the training error is, let's say, 0, and then this term is, let's say, 1,000,000. So it's a calculation, but it is not a theory for why even machine learning works. And this is nothing specific about neural networks. So random forest, you wouldn't be able to put them into this formula at all. But this is widely believed to be a very clear indicator that we do not understand generalization. 30 years of working with these kinds of formulae are just like useless when you think about neural networks. And obviously the stuff that is complicated is this term, because the weight space is huge. You cannot control the complexity of the models. In fact, the models are universal approximators, so they can't fit anything. They are very complex. So the way to think about this, at least for me personally, is not to find different ways to build a bound like this, but to find different ways to calculate this term in a smaller set of models. Okay. You can also think of the right-hand side as a Bayesian information criterion. So to pick models for the purpose of model selection using a combination of training error and complexity. And that is how people have also used them a lot. Let us look at one very simple calculation. So this is the training error, E hat n of Q. And I threw away the square root on top of this. So you can think of this as an upper bound on the PAC-Bayes or a very loose PAC-Bayes bound. And I would like to calculate Q now. I will assume that my prior is something that is a Gaussian that is centered at the initialization W0 with some scale parameter epsilon. And I'm going to calculate Q, which I will also assume to be a Gaussian centered at some weight W and a covariance matrix sigma Q. It is not very difficult to show that the covariance matrix of this distribution Q has the same eigenvectors as the Hessian of the network at the location Q. Because of course, the Hessian tells you which direction the loss doesn't change too much. Those are the directions in which Q should put a lot of probability mass so that it eats a lot of stuff from P and reduces the scale, but doesn't get hurt in terms of this training mass. Okay? And the opposite is true for the large eigenvalues. Q should not put a lot of mass on them. So the eigenvectors are the same. The eigenvalues actually follow this exact logic. The inverse of the eigenvalue of the distribution Q is proportional to the eigenvalue of the Hessian. So larger the eigenvalue of the Hessian, smaller the eigenvalue for the distribution Q. Doesn't put a lot of pass. Okay. The surprising thing is that even just this little calculation already gives you a bound that is less than 1, that is not vacuous. So for a two-layer fully connected network on MNIST with about 600 hidden neurons, the PAC-Bayes bound using this analytical formula is 0.32. And that is why I said that this is the first analytical non-vacuous bound. You have to still calculate the Hessian to implement this bound, but I can write down the bound clearly. Okay, and so this is a very tiny calculation, to be fair and honest, but people just did not notice that it already gives you a good result. Okay, this is what some people call like a post hoc bound, where you say, I am not saying that this is a good bound on generalization for every Q. I'm plucking out a Q for which the bound is a non-vacuous. So this doesn't show that every time you train a neural network, you get good results, but this does show that there exist networks which can give you good results. So in some sense, this is not that surprising. In some sense, it is surprising because it is this simple to show that there exist neural networks that give you good generalization. The real meat, I think, would come if someone can show that every time I train a neural network, I reach locations like this, which is very hard. Here is another way to use this calculation. Again, a very simple one. Look at this eigenspectrum. We like to think of the elbow of this eigenspectrum, the stuff where the log linear part begins, as a special point. This is a point where the PAC-Bayes distribution Q switches its mentality. Instead of reducing the probability along the large eigenvalues of the Hessian, it finds these sloppy eigenvalues of the Hessian and decides to put a lot of mass on it. Okay, so we can take this threshold and then call these a number of eigenvalues to the left of this threshold as some kind of effective dimensionality of the model. As a formula, it looks like this. So these are the eigenvalues of the Hessian. The absolute value of the eigenvalues is greater than equal to epsilon, which is just some parameter for the prior that is not really important, divided by 1 over divided by 2 times n minus 1. And this is a very useful formula because if n is very large, it is infinity, then this formula tells you that your neural network is using all its parameters as degrees of freedom. This makes total sense. If you have an infinite amount of data, then you need a lot of parameters to fit that infinite amount of data. If your data is small, then automatically the effective degrees of freedom is less. And that is also very useful. There is 2 kinds of capacity control occurring because of data. One is the fact that you don't need to worry about the small eigenvalues because these things drop very quickly. It is coming from the shape of the data matrix. The second one is coming from the number of samples. Fewer the samples, automatically smaller the degrees of freedom. Okay. In fact, like for essentially most networks, you can check the effective dimensionality is about 0.5%. Most times even smaller than that. So when you train a model with 1 million weights, you really like are training something with about 5,000 degrees of freedom. And now it doesn't look that surprising that you can fit this model with 50,000 samples of endless. With augmentations, they become more like 200,000. So you can use this as a proxy for like model selection, lots of stuff with it. This is not the only way to define effective dimensionality, but it seems like a reasonable. If you kind of just crank through the calculations again, typical generalization bounds will go like this. If P is the number of parameters, you will get like a P over N. N is the number of data points plus some square root term of P over N. The PAC-Bayes bound can be written down in like a non-Bayesian way as a square root of the effective dimensionality over N. Okay. So basically you can replace all formula that you see in uniform convergence by P of N comma E epsilon, and stuff still remains meaningful. Just to give you some numbers, so this is a 3-layer network with 600 neurons. The effective dimensionality is 2000. The VC dimension is about 60 million. So there's a huge gap in how we measure things if we consider the space of all functions versus we consider the space of functions that could be fitted on such kinds of data. This is what you this is the clear benefit of data not being very complicated. I think I'll actually skip this slide, but maybe I'll say it in one sentence. So we have noticed that neural networks typically train in the stiff dimensions of the facial information matrix, and they don't train very much in the sloppy dimensions. This again makes sense. The sloppy dimensions don't change your output too much, so why go there? The gradient is already small.
Yeah, I was just going to ask one question about that, which I could ask later. When you look at trying to do more Bayesian neural network training, like Bayesian ensembles, you're trying to generate other networks which have similar loss. And it seems like the sloppy dimensions would be sort of good for generating ensembles because you can change them a lot and still have similar loss.
Yes.
But are they useful in the sense that they have similar loss, but different samples are the loss, the sort of errors are in different samples?
Yeah,
or are they kind of useless and it's really all the action is in that stiff subspace?
Yeah. So
and if you want a good Bayesian ensemble, you actually want to sample from the stiff subspace.
Yeah. So sadly, like the ensemble where you are changing the sloppy dimensions is useless because it doesn't change the function too much.
Right. The function doesn't change, therefore the prediction.
Yeah. And this is also something that the Bayesian machine learning world has discovered, that the ensemble is really not diverse. And what I would like to claim is that it can never be, because there is only one way to fit this data. There are not too many different ways of fitting this data, so the different members of the ensemble are really not diverse. You cannot sample the stiff directions also, because then you wouldn't fit the data at all.
Right. Because if you move them, your loss will
so
go up.
The manifold of functions, it looks like a little ribbon, a hyper ribbon in a space of functions. One corner of this ribbon, or one side of this ribbon, is the model that fits your data. So you cannot sample the other side of the ribbon. You would find a really bad model, chance accuracy model. But the width of the ribbon is the sloppy directions, and those don't do anything. So in some sense, Bayesian neural networks are not really necessary. Okay. I mean, so there is much more nuance to this sentence than what I said, but they're surprisingly not entropic, the posterior you find. Okay, I think I moved my hand. Yeah, so I created the labels using such a teacher, and then fit the data set created labeled by the teacher using a student. So this student only has 10 neurons. This teacher has 100, and then you can also have a student with many more neurons, etc. So this is a very classical teacher-student setting that you will see in all the calculations. So there are 16 different experiments here, 16 different data sets, teacher-student combinations. Every single model, every single student interpolates the data. So every single student has 0 training error. Okay. And this is not surprising because even if the student is so much smaller than the teacher, because I'm not giving it infinite data, it is finite data, it should still be able to fit it. Okay. What is surprising is that if the slope of the eigenspectrum is large, then the students that interpolate still generalize. If the slope of the eigenspectrum is small, then the students that interpolate do not generalize. And this is a very clear demonstration of a benign overfitting phenomenon. It is true not just for linear models, like in Bartlett's paper, but also for nonlinear models. If you have data that does not that is not sloppy, then you need to give me lots and lots of training samples before I can meaningfully generalize. And it is exponentially many samples. So that is really where you see the curse of dimensionality happen. Here it doesn't happen.
I assume that in that plot, sorry, the training error goes to 0, so that when the validation error is large, it means you generalize poorly.
Yes.
Okay.
Yeah. The training error is 0 for everything.
Okay.
Yeah.
Makes sense.
Okay, so here is my mental picture of how the network trains. Imagine this slide as being the space of functions. The fact that the Fisher information matrix is sloppy tells us that there are some directions, the stiff directions, which are the long ones on this little manifold, are the dominant ones. So training typically begins somewhere. You initialize your model as a function, and then when you train, you reach like a point that is closest to the true function of data, right? Your neural network may or may not be able to represent this true function. So you'll find the closest point on the manifold of the network that is to the data. So training typically occurs along the stiff subspace. The sloppy subspace are really like these thin directions to the manifold that don't do much. You can move along them and you will get tiny improvements. So this is like you having a blue dog in your data set. If there is a couple other blue dogs in the validation data set, then it makes sense to fit it, but you don't lose out on too much by not fitting the blue dog. The stuff about a Bayesian ensemble. So when you train a neural network now, if you believe this picture verbatim, then you will find your members of the ensemble as like a little cloud around this green point. So the only way that they would be different is in the thin directions. You cannot sample a point here. I guess you could, but that won't be a very useful member of the ensemble to begin with. Okay. Maybe I can spend 5 minutes on this. So this is another paper that I wanted to just give a sneak preview of. Think of it as an application of this entire business, a very useful application. So this was done by Yansong Gao, who is just about to finish his PhD, and another student called Rahul Ramesh, who is in computer science. This is also an archive if you want to read more. So let's begin with a very simple experiment. Okay. I give you a biased coin, and I would like you to estimate the bias of this coin. You are a Bayesian person, you will say that I have a prior that I put a uniform prior on 0 to 1, and then I toss my coin an infinite number of times, and I localize the prior. Because the prior is a uniform distribution, you need an infinite number of coin tosses if you want to precisely estimate the bias. There is no mystery to this. What I would like to ask is, suppose I told you that I am only going to allow you one coin toss, okay, not infinite, just one. What prior should you pick? You clearly should not pick the uniform prior, because it puts mass on many different models. You have only one bit of information to distinguish between that, right? Turns out this is a very well-studied question in very old Bayesian statistics, when people really got upset with the subjectivity of priors, and they said, "Oh, we want priors to be more objective," and yet non-informative. So they started thinking like this. For the case of a coin with one coin toss, a good prior to choose is something that puts half probability on 0 and half probability on 1. It is a useful prior because as soon as the coin lands heads, I know that I should just predict this as the bias of the coin. Or if it lands tails, you know that you should predict this as the bias of the coin. So there is something very deep going on here. So you know that the parameter space has a clear boundary, 0 and 1. You know that the outcome of the coin can only be heads or tails, nothing in between. And that is why you choose a prior like this. So you know that you're going to get one bit of information. So why would you pick a prior that puts probability mass on more than two possibilities? Because you wouldn't be able to localize them anyway. If you have two tosses, then you put your mass on a slightly more number of possibilities. Okay, so this is called a reference prior. Reference priors are priors that maximize the mutual information between the weights and the data while knowing the number of samples that you're going to get. So when we apply Bayes' law, we typically do not care about how many samples you will get to calculate the likelihood. The concept of reference prior says that I understand that the data is always finite. So I'm going to pick a prior that makes the maximum utilization of the finite amount of data. And a very intuitive way of thinking about this is that I want to pick a prior such that the posterior, after looking at the data, W given Zn, is maximally different from the prior. So this is a very different way than how machine learning people think. Machine learning people, or even a part of the statistics community, says that I have data could be noisy, so I will pick a prior that reduces the effect of noise on the data. This is totally valid, totally reasonable. But if I don't have too much data, then I have to trust the data. So I want to pick a prior that lets the data dominate posterior as much as possible. There's two totally different philosophies of thinking about Bayes' law. And this is very interesting when data is very little. Okay. So this is this is called a reference prior. You pick a prior that maximizes mutual information with the weights of the samples. Okay. Here is how the prior looks. So this is a visualization technique that we have been working with. Basically, you can think of it as a neural network. When it fits some samples, I can look at the logits of every sample in my training data set and think of this as a feature vector. So for CIFAR, there's 50,000 samples, 10 logits per sample. I can think of a neural network as a vector in 500,000 dimensions. It is a slice of the space of functions, right? A function is infinite dimensions. This is a finite dimension slice of the function. And now I can do PCA on this vector. So I take many networks and I do a PCA of such feature vectors of these networks to study how different the different networks are on the data set. And here we are doing this on 3,000 particles. So remember that if I want to represent a prior like this, I need 5 particles in this case, the number of atoms. Reference priors are always discrete for finite data, so we can always represent them using particles. We don't have to use a variational approximation. So we used a prior with 3,000 particles, and then we optimized this prior to solve a binary classification problem on MNIST. The blue parts is the beginning of the training process. So we are using Blau-Terremoto on these particles to optimize, to maximize the mutual information. So this is just where the optimization begins. And as you keep on fitting the prior, all these particles, the blue points, they move far away from each other in the space of functions. These are the top 3 principal components of this weird 500,000 dimension vector. So what that tells you is that the reference prior finds atoms that are maximally far away from each other in the space of models. When you look at this picture, it is not that difficult to believe. These 2 atoms are maximally far away. These 5 atoms are also maximally far away as far as like the data is concerned. If you have an infinite amount of data, the reference prior converges to Jeffrey's prior. So everything is well and fine in infinite data. Okay, so this is how these priors look. Now, if you remember my picture of the training process, a true data set is one point in this space of functions. The particle that is best suited to make inferences of the true point, true data, is one out of these green particles. But the green particles are like spreading apart like any good prior should, without spending too much attention on parts of the space that don't matter too much. These interesting parts of the function space seem to be some kind of a boundary on a manifold. Okay, this we don't really understand very well. And here is one way to use this. So we think of this as a formalization of semi-supervised learning and self-supervised learning, because at the end of the day, all semi-supervised learning is saying that I give you some unlabeled data, you cook up a prior using your unlabeled data, and then I give you some labeled data, do your inference, and that's your posterior. Okay. So if you build a reference prior for classification, it has this very interesting formula. Focus on the second term. So W is one atom of this prior. H of yu given xu are unlabeled data points, yu are the predictions of the unlabeled data points made by the network, made by W. So I should actually also add a W here on the right hand in the conditioning. This is the entropy of the predicted logits for the unlabeled data by every atom. This stuff is being maximized. So every atom, every one of those green particles, they like to make very confident predictions on my unlabeled data. Of course, they don't know the true labels, so this can be confident and very wrong. But the point is that together as an ensemble, they are being very diverse about it. So this is the marginal over W, and it is the entropy of the complete posterior or the complete prior of the green particles and their predictions. So the entire prior would like to make very diverse predictions from each other, but every damn particle wants to be very confident. So you're wrong and confident, and together you are very diverse. And this is why these particles go to very, very different parts of the parameter space, because they want to be very far away from each other in terms of predictions. Okay. So if you implement this formula, or if you stare at it long and hard, you will see that you can derive many existing semi-supervised and self-supervised learning algorithms from this. They are implementations of this formula. So when people create an ensemble and then they say, oh, I want to make sure that the different particles of the ensemble disagree with each other, this is the first term. When people create augmentations and they say, I want two augmentations to have very different representations, that is again the first term. Okay. And this is so in the paper, we kind of take a bunch of recent algorithms and derive them using this formula. In fact, if you implement the formula just like this, you can essentially match the accuracies that these very fancy and performance state-of-the-art methods get. So for CIFAR, with 5 samples per class, you are getting 85% accuracy. So all the other samples are unlabeled. They are used to build a prior. And this is telling you that you have a reasonable way of thinking about self-supervised learning or semi-supervised learning. And not only is the formulation clean, but it also perhaps faithfully reflects what these other algorithms are doing. It has very beautiful connections to other areas. We can talk more about it. But to summarize, there is many mysteries in deep learning over the years that we have discovered. Maybe they are not due to neural networks. Maybe they are because of the data. So stuff that we attribute to regularization, stuff that we attribute to fancy tricks in optimization, they could all be explained perhaps by simply studying how they relate to the properties of the data. Okay, and it is shocking to me, like how strong the structure of data is. And if I were to go out on a limb, I would say that typical problems are perhaps simple. So the reason we gave this bunch of molecules a name, chair, is because we wanted to recognize it in some other scene. And we may not have named it a chair if we did not care for using it. We may not have named it a chair if there were too many diverse chairs. If there was no structure in the physical world, then we wouldn't have created objects. So we create learning problems because we can learn them. And in some sense, we throw away all the stuff that we don't care. So for something like for a physicist who is used to doing renormalization analysis or so, this is a very natural way to think. You want to build a theory of some behavior. You don't care about this microscopic stuff that happens below it. But if you want to understand the microscopic stuff, then you need to build a different theory that goes one level down. So this is a way to say when we can learn and when we cannot learn. So maybe like the stuff is actually simpler than what we think. The world is engineered in a way that we can learn, and that is why we can learn. So we should be less cocky about our progress in deep learning. I am the speaker. This work was driven by a number of very interesting students. Some of them are very young. So Anirudh, for instance, he did the first experiment that showed us that the Fisher matrix could be related to the data matrix, and he was in his first year of undergraduate when he did this. So we are an exciting group. They keep me occupied. If you want to read more, these are the papers you can look at. Thank you so much.
So there's one question in the chat. So after training, can we compress the model and get rid of the sloppy subspace?
Very nice question. So the short answer is no. And the small eigenvalues of the Fisher, they are combinations of the weights. So you want to set combinations of weights to 0. And yes, you will be able to set them to 0 without losing a lot of predictability. But that doesn't mean that the bare parameters, the weights, will become sparse. So in fact, we've done these kinds of experiments. If we compress the Fisher by throwing away its sloppy subspace, the network is still dense. Maybe the dynamic range of the weights reduces a little bit, that I haven't checked, but you cannot cheat by compressing the model. This is why, like, everyone after the lottery ticket hypothesis, people are trying to search for, oh, maybe there is a clever way to train, and then there is no clever way to train. You have to train in this large space. There is I also get a similar question that says, oh, if the data is sloppy, can we throw away the smaller eigenvalues in the data? Again, no, like, because the blue dog lies in the sloppy space. If you don't care about the blue dog, sure, throw away those eigenvalues. But the entire point is that the salient parts of the data belong to the stiff subspace, and the non-salient parts, which we may be interested in because we are interested in a diverse kind of data, lie in the sloppy parts. So we cannot throw them away.
And there's also one follow-up question also by you. So there are lots of models in the reference prior, which is expensive. Could this be relaxed to a continuous?
Yeah, so in principle, the reference prior number of atoms need to be huge. It cannot be relaxed to a continuous prior because the prior, as you saw, was decidedly discrete. There is no variational approximation to a distribution that looks like this, that still keeps it meaningful. What we have found in experiments is that even 2, 3, 4 particles is enough. So for instance, I think in this table, we are using 4 particles. And the reason for this is that really, like, the few labeled data, so the 5 labeled samples of CIFAR that you get, they already pull you pretty far close to this green point. And then the 4 particles that you have spread around a little bit. If you did not have any labeled data to begin with, if you were simply like implementing Bayes' law very religiously and first building a prior, then you would have to spread apart on the entire manifold, and then your 5 labeled samples will pick one part of this. But you can actually cheat a little bit by optimizing the prior and the likelihood term together. That way you reduce the part of the space that you have to search over, and it's like your problem becomes much smaller. So in practice, we have basically the same results with 2 particles also. And this is something that we're fighting a lot with reviewers with, because they're like, oh, why can it even work with 2 particles? It does.
Yeah, yeah, maybe I misunderstood how it works. I thought you first optimize those discrete reference priors, and you're saying
that is, yeah, so that is the proper way of doing things. But you can kind of write an objective, which is the mutual information using the unlabeled data plus the likelihood using the labeled data, and just optimize them together.
I see,
Yeah.
okay,
So you implement Bayes law just differently.
right. Okay, I think I see what you mean. It's sort of like using the reference prior idea to motivate a regularizer, which does something similar.
Yeah, so I don't like to call it a regularizer, but sure. I think of the likelihood term as a way of reducing the surface for the pattern. And we still actually implement the Bayes predictive distribution, Bayes predictive formula on the particle after fitting the particles.
Right, because you want your models to be maximally different.
Yes. But there is so many ways of being very different. So we need to control like how much they move. And these tiny few amounts of label samples tell you which parts of the space is good. And really like the honest way of thinking about this entire business is that five samples per CFR is huge amount of information. So that is why these methods work really.
Yeah, I think these are all the questions on chat.
I guess we've gone pretty far over our normal time. Does anyone else have any questions? Yeah, I think we'll stop because we can continue our conversation. Thanks everybody for calling in. Thanks again, Pratik, for really super informative talk.
Thank you.
Thanks.